All right, we are now moving on to problem number 32. So it is based off of the same diagram from above with the same situation. A particle of mass m moves counterclockwise around a horizontal circle of radius r as shown above. The angular speed of the particle is given as a function of time t by omega of t is equal to bt, where b is a positive constant and t is greater than or equal to 0. What 32 wants to know is what is the magnitude of the angular momentum of the particle about the center of the circle as a function of time. So, if we think back to what angular momentum is, angular momentum is the moment of inertia of an object times the angular velocity of that object. So so we have our we have we have our moment of inertia, I, times omega, and that is equal to our angular momentum, which is L. So our moment of inertia is just going to be mr squared. But our omega, our angular velocity, we have a function of t for omega, which is exactly what we want because we want the angular momentum to be a function of t. So since the angular momentum is dependent on the angular velocity, it's really good that that's a function of t. So we have mr squared as the moment of inertia times omega, which is bt, and we get mbr squared t as our angular momentum. So if we go down the line, A is mbt divided by r. That doesn't really make sense, so it's not that. B is mbrt. This is almost correct, except the r isn't squared, and for moment of inertia, the r has to be squared. C is mbr squared t, so that's exactly what we want. So the answer is C, mbr squared times t. And if you want to see the math, it is right there. Very simple, this one. Just a function of a function. Now, if we had a different sort of shape as our orbiting mass, we would, of course, have a different moment of inertia, and the answer would be different. But since we just have a particle of mass m rotating or orbiting with a radius r, that makes the moment of inertia just mr squared. And whatever the constant b is will affect this first of all, the rate at which the angular velocity changes, as well as the therefore the rate at which the angular